Alright guys, so let's talk about the age of the Earth and how we know how old it is. It's something that comes up quite a bit when we start talking about Earth science or the evolution of the ocean even. We need to take a look at how old this is and how we know. Alright, one of the biggest clues we have is when we find meteorites. Meteorites on Earth were formed when the solar system began. And as the solar system began and they hit these meteorites, we can take them and radioactive date them, and they go back to about 4.5 million years ago. So it gives us a good opportunity to take a look. This gives us a lot of opportunity to show what a lot of these iron core meteorites are a great basis for how old the Earth is, just generally speaking, when it all began. If we look at the geological time scale, you can see that 457 million years ago, this is where the sun and the acceleration of the sun began. Now, we're not talking about the formation of the universe, the Big Bang. We're talking about the sun beginning to form. As we go through the timeline, we don't see earliest life until about 350,000 million years ago. So we start getting into bigger, and you can see if we go all the way past here and look at where man began, he's only 5 million years old. The last mass extinction being about 65 million years ago. And if you look through this, you see that there is a ton of mass extinctions that have. It also highlights the evolutionary Big Bang, and that's where many multiple creatures begin to form, and we start to see a lot of different creatures begin. Alright, but the Earth, when it began and formed and started to cluster, all that extra mass that was left over from the sun that the sun didn't use just became this huge bombardment. The Earth was knocked together and plowed together by all these extra stuff that the sun never used. A lot like meteorites now that once in a while come in, but you can imagine that on a mass scale happening constantly. We also think of the formation of the moon. The Earth began, it started to form, and then it was hit by something really big, almost 50 million years ago. And when the Earth was hit, it was hit so hard that it actually split the Earth. As it split the Earth, you can see the simulation. Whatever that impact thing was, it was huge. It hits it, mass ejects all of this extra mass off of the Earth, and then over time, the Earth reforms itself into the sphere that we know, and that extra junk that was left over out there forms the exact same way as Earth did, and we end up with our moon and our system that we see now today. Formation of the moon. It continues to be bombarded, and because it has no atmosphere, we can see those craters and how it was hit. So that continues to happen today, not as frequently, and I don't think that we've ever even seen it truly happen, but we know the evidence is there, and with a lack of atmosphere and erosion, we can see the entire history. Earth's not that way at all. Earth covers up its marks with its erosion and moving water and wind, etc. Alright, so with the early Earth, once we have that, we've got the moon beginning. The early Earth is very hot, very molten. It compresses down and gradually cools. And the radioactive elements like uranium, potassium, thorium, all of them are there as well and present, begin to sink though. So we have the heating and the melting occurring here. Okay, once this happens, the heavy metals fall to the center and forms the core. Now that happened about 100 million years ago, or 100 million years after the initial acceleration of the temperatures. And the deposits are 400 to 800 kilometers below. So we see this begin to form in the core, and then everything on the outside is a much lighter element. Okay, so we look at it, you have this hotter core that condenses in. Once it collapses down, we get the solid iron to the inside. You have more of a liquid iron on the outer core. The mantle is, of course, molten rock, and then our crust right above that. So we end up with these different layers that we talk about quite often. And it's about 4.3 billion years ago that this began to happen with the inner and outer core, along with the mantle and the crust forming. All right, the composition. If we look at the whole Earth, it's primarily made of iron, oxygen, silicon, magnesium. About 93% of all that is made of those things. The crust itself, however, only has silicon, oxygen, and aluminum in it. So you can see where the heavier metals like magnesium really sank to the center and fell in, iron down to the middle. That's why we assume that they're in the core, because that's the only place to account for them. They're just really not that present on the core. Or on the crust, I'm sorry. All right, different layers that we need to know and talk about. We have the lithosphere, which is the outer, strong, rocky outer core, so it's like a shell of an egg. Just below that, we have the asthenosphere, which is weak and ductile, means very soft, very malleable, moves. The deep mantle, which is beneath the asthenosphere. The outer core, which is mostly liquid. And then the inner core, which is that solid iron that collapsed into the center there. All right, chemical composition of a lot of these eruptions. We know what's in the core. We know what's in the mantle, mainly primarily because of the eruptions. So if you find an iron or any of those other elements up on the surface, it's usually because of volcanic eruptions that have pushed it from the center out. Naturally speaking, a lot of those things like carbon dioxide, nitrogen, hydrogen, and of course water, which is the big key here for oceanography, is ejected in these huge volcanic eruptions. And that's where we believe a lot of the water formed is from these volcanic eruptions. All right, then along with that, with the water, as the water comes on, mostly because we have some extra helium and some hydrogen, these gases are able to form our atmosphere that we know. Early atmosphere wasn't anything like what we see now. It was probably closer to something like a Mars, a very thin, easy atmosphere that didn't protect the Earth very much. So that started to change and become evolutionary as these eruptions occurred and more water ends up in the atmosphere. Continues to happen, of course, with these big eruptions, throwing up the different sulfur and the different gases, nitrogen, carbon dioxide, etc. A lot of this evolution, we see the water vapor, which is the big one, sulfur dioxide, hydrogen sulfate, carbon dioxide, carbon monoxide, ammonia, methane. All these come from these volcanic eruptions early on. So as this stuff's blowing up into the atmosphere, it helps to actually push up. And a big note I want you to notice is that this early atmosphere really doesn't have any oxygen in it. All right, as the oceans create, what is hypothesis is the water vapor escaping from the interior of the Earth. So we have that water in the inside, escapes from volcanic eruptions. And you can imagine how big those eruptions must have been to form these huge oceans that we see today. And it would have taken millions and millions of years for this to occur. All right, with the atmosphere, it's hypothesized again that comets impacting the Earth were a major source of the water. So we also got it from the comets to hit the Earth with water in them because they're mostly primarily made of water, ice, and gas. And that contributed to the oceans as well. Basically, a comet comes down to being a dirty snowball. All right, and earliest evidence of the surface water on Earth dates back to about 3.8 billion, and that's, of course, erosion and these kind of things that we can go back and look. Grand Canyon is a great place to see this. Can you imagine that 3.8 billion years ago was the first time that we ever see water on the surface? All right, back to that geological time scale. Now we have the earliest evidence of life. So here, 380,000 years ago, we see the earliest evidence of water. And then you can see it takes another 3,000 million years for first evidence of life to even begin to show. All right, so 3.5 billion years ago, the Earth was a thick atmosphere, mostly CO2, methane, so it would have been, I guess, more like Venus, more so than Mars. And remember that only about 20% of our atmosphere is only oxygen, so very little of the atmosphere has oxygen on it at all. All right, the Earth also had an extensive ocean and seas, so it would be a majority of water. As we study oceanography, we'll see how much of Colorado and this middle corridor right on the United States was an ocean, actually. And that's where it dissolved a lot of iron. That's where you see that red rock down by Colorado Springs and in different parts of Colorado and Utah. That's iron. And it was deposited because of the eruptions and the water formations early billions of years ago. All right, but the most important thing is remember that by 3.5 billion years ago, there was life. It was very simple, very minute, minuscule life. It was very primitive, but it was beginning to take hold at this point. All right, so this is the end of part 1 for this second unit. Make sure you have your notes, get them checked. Check the next lab that you have to take care of. All right, see you later.